Hello. So this unit is going to be on plate tectonics. It's going to be kind of a quick overview of what you have already learned before. I'll also add some additional supplementary information just in case you're curious or would like to go over something a little more. All right, so plate tectonics. Essentially, it's the movement of tectonic plates. So the lithosphere, if you remember, we talked about it in our previous unit. The bottom part of that is going to be sitting on a liquid upper mantle called the asthenosphere, and then the top part of that is going to be like what we walk on, like the continents. So the lithosphere is divided into tectonic plates. It's not just one big piece of land. It's many pieces of land that have moved throughout the history of the Earth. So the theory of plate tectonics is just the theory describing the movement of the Earth's lithosphere and those pieces of the lithosphere. They move at about 3 centimeters a year, which is a lot of movement if you're thinking about like hundreds of millions of years. So, you go hundreds of millions of years times 3 centimeters, and that stuff has moved thousands of miles. So that's just something to think about. A lot of the times with earth sciences, we're talking about things that happen over a long period of time. So what happens at tectonic plates is that they interact at boundaries. We get earthquakes and volcanoes happening at those boundaries. And then the different types of boundaries are called convergent, where they're converging, so they're moving together. They either have a subduction zone where one goes under the other due to density, or they form a mountain ridge. So if they have the same density, they do this type of thing. And then we've got divergent, so they're diverging, so they're moving apart, so they're going like this. And then we have transform boundaries, or also known as strike-slip faults. So what's happening there is they're moving from side to side. So they're kind of going like this. They're meeting and then moving. One's moving one way and one's moving the other. So that's just a lot of energy that they have to kind of control. So when you get a lot of energy and these plates are kind of hitting each other, they have to go somewhere. So they end up moving this way, or they smash into each other. All right, and so here are the plates. We've got the North American plate here and the Eurasian plate here. And then we've got the Pacific plate, which goes between the Eurasian plate and the North American plate. So any flat earthers out there, I am sorry to tell you, but it is a circle. This Pacific plate hits the Eurasian plate on one side and the North American plate on the other side. So that wouldn't be able to happen unless the Earth was round. All right. So here are just the other boundaries, the boundaries that we talked about. We've got divergent moving away from each other, convergent converging, hitting into each other, and then transform or strike slip, moving sideways, the opposite direction of each other. Okay, so how do they move? So we talked about it in the previous unit a little bit. So on the asthenosphere, it acts as a liquid. All liquids and gas go through these things called convection currents. So essentially hot goes up, cold goes down. And so we get these currents in here due to magma. Hot magma moves up, it goes up, it gets pushed over, it cools down, it comes back down, it heats up, and it does this cyclical movement. So what's happening is this convection current, as it moves to the right, in this example, this little plate here, this tectonic plate that is sitting on top of the asthenosphere, is going to move to the right where it contacts that asthenosphere. So it's going to be moving to the right. Down here, it's going to be moving to the left around the Earth. So the edges of the plates right here and right here, they cause subduction zones, rifts, and faults. So rifts are going to be at divergent plate boundaries. You should write this down. Rifts at divergent plate boundaries, or ocean trenches. Faults are going to be on pretty much any boundary. Subduction zones are going to be at convergent boundaries, where an area of more dense rock, usually oceanic crust because it's more dense, hits continental crust. It hits, it pushes down. That's a subduction zone. And then there's mountain ranges at convergent plate boundaries, and that should be it for those. Okay, so here's the Ring of Fire. We're going to talk about, this is where pretty much most of the volcanic activity in the world happens. There's also an Atlantic island arc that is also kind of a ring of fire, but this is where most of the volcanic activity occurs. And so what's interesting about this is this here, this area where there's no ring of fire, is the Pacific plate. And so right here is the North American plate. And so where they meet along these zones, this little red area is where the Pacific plate right here meets the North American plate. And so when we get these convergence or divergent zones where plates meet, that's when you see a lot of earthquake or volcanic activity. So, and also mountain ranges. So you're going to see where plates meet, you're going to see a vast, vast majority of earthquake and volcanic activity on this earth. So we'll go back and I'll show you right here. Here's the Pacific plate. It's meeting the North American plate right here. It also meets the Eurasian plate and the Philippines sea plate. But a lot of the times you're going to see right here is where that ring of fire is, where we get these two, we get like a continental boundary meeting an oceanic boundary. Okay, so plate tectonics also affect climate. So the continents used to be one large supercontinent called Pangaea, and this is Pangaea here. We have evidence of this in the fossil record, but it started with an observation. So someone looked at all of the continents, and they said, hey, South America looks like it could have fit right here in Africa. Africa looks like it could have fit right here in Antarctica. India looks like it could have fit right between these two, and Australia looks like it could have fit right here. So they saw this observation, and then they looked at the fossil record with index fossils and relative aging of rocks. So rocks, they store information about climate. And they looked at what time in these rock layers they found these index fossils. So they found this fossil of some lizard in South America, but they also found it in Africa, the same species at the same time in that rock layer. So they can accurately judge that this area right here was of the same rock and was there at the same time. So otherwise you would get different species in these two areas because it's a vastly different climate today than it was hundreds of millions of years ago. And then Antarctica, it has all sorts of stuff spread out throughout all of the continents. And what we know about Antarctica today is that it's pretty much a wasteland. There's not a lot of life going on there. So to see life, evidence of life here in Australia, India, Africa, South America, that's really, really good evidence that these continents were together at a certain point in time. All right, so land masses affect climate. Essentially, land masses have a lower specific heat than water, and it's also called specific energy. So essentially what's happening is in the winter, it cools down much easier than oceans, and in the summer, it heats up a lot easier than oceans. The continents do. So they change temperature more quickly. That will change climate. And mountain ranges have this orography, which is just rain shadows. I'll show you right here. Mountain ranges can create really strange climatic events. So we get this warm, moist air and prevailing winds pushing this cloud up and condensing up into here, making precipitation happen up on say this is the Rocky Mountains, this would be the north face. And so it's going to get a lot of rain. You see a lot of trees, a lot of vegetation on the north slope of the Rocky Mountains. And that's because this warm, moist air is getting pushed up. It hits a certain point, it cools, it becomes denser, and it has to fall. So it falls on this north slope of the Rockies. Then we get precipitation at the top, and that's snow. And then it loses all of its precipitation going over. So what happens then is we get dry air. Usually it's cool, dry air coming down on the opposite slope of the mountain. And then we get a rain shadow, which is just like a little bit of rain. It's not anything significant. So you see that in the Rockies, where the north face is really, really, really high in precipitation and vegetation. And then I think it's actually the western slope, is really dry and kind of like a desert. All right, so oceans and climate. Like I said, they have water has one of the highest specific heats in the natural realm. So water is the ocean. So the climate is affected by the oceans, and I'll get into that real quick. We've got the Gulf Stream, El Nino events, and currents kind of dictate what happens in El Nino and the Gulf Streams, and that depends on the connectivity of oceans. So if oceans are blocked off, there can be no current, so there can be no Gulf Stream, no El Nino, that sort of thing. So northwestern Europe is warmer than other regions at similar latitudes because of the Gulf Stream. And that's right here, this warm water. This is called the ocean conveyor belt, I believe. But essentially, it's just kind of a convection zone. You can see this warm water is going to move up. It's going to get cold right around Greenland. It's going to fall back down, and it comes down straight to Antarctica, creates that Antarctic environment. It gets warmer as it gets towards Australia, New Zealand, and then it goes up and up and up. It gets hotter, 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 and then this little weird conveyor belt action goes on. So if these continents were together, we wouldn't have this same flow. So imagine if South America was here in Africa, we wouldn't have any of this. So Europe would be very, very cold because this Gulf Stream here is bringing up a lot of warm water, and it's creating this habitable zone right here in Europe. So Greenland is not habitable. People live on it, but it's just like Antarctica. It's not very feasible to live there for extended periods of time. And so the reason why there are a lot of people in Europe is because of that Gulf Stream and that convection zone. So that's how the oceans can kind of dictate climate and how the currents dictate climate in the oceans as well. All right, so earthquakes. Plate tectonics cause earthquakes. So the shifting of plates trigger earthquakes. They get stuck, which that's a very unscientific term. They essentially, like with convergent plates, they're hitting each other, and there's this massive buildup of energy. And essentially, what's going to happen at a certain point is one's going to either go under or they're going to smash up. And so that takes a long time, but there's going to be an event where when they move up a little bit, that's going to release a ton of energy because there's a lot of mass involved in plates. And so with all that mass, there's going to be more energy. And so when that energy gets moved, so when those plates move, energy is released. And essentially that's what seismic waves are, is just a release of energy. So they break free when the shifting of the plates happens, and then you're going to get this release of energy, and that's an earthquake. And so a tsunami is it's an underwater earthquake, but really what it is huge waves caused by the energy of seismic waves. So you're going to see liquid water moving at about 500 miles an hour, up to 500 miles an hour, which is humongous. And so when you see tidal waves and tsunamis hitting coastal areas, it causes a lot of devastation because it's kind of hard to tell when it's going to hit, and then when it does hit, it doesn't really matter because there's so much energy in that system being pushed into your coastal wetland. So here's a picture of an earthquake, a fault. This is a fault that happened due to an earthquake. And then we've got volcanoes that happen on tectonic boundaries. We talked about it with the Ring of Fire, so I'll go over it just very quickly here. They happen at an opening in the Earth's surface, either a subduction zone, which creates like a melting rock. As this rock goes down, it melts, and then it comes back up and then goes through a hole in the Earth and creates a volcano. Or you get a divergent boundary. So when it opens up like this, then you're going to get the ability for magma to infiltrate that area and create a mountain, which is a volcano. So magma, ash, and gases escape from volcanoes. They're found where tectonic plates diverge or converge. And then also we get hot spots where the crust is just thinned out and there's magma coming up through the surface. So that is an example, like the Hawaiian Islands are going to be a hot spot. And so that's just really the crust. The bottom layer of the crust has opened a little bit, it's thinned out, and some magma is coming up through that little hotspot zone. And so volcanic eruptions emit a lot of toxic gases into the atmosphere, greenhouse gases and just toxic gases. CO2, sulfur dioxide is toxic. CO2 is just a really bad greenhouse gas, and then you get ash. So right here, this volcano is emitting a crazy amount of CO2, sulfuric dioxide, and ash, and that's going to go into the atmosphere and kind of screw up a lot of things in the atmosphere. It's going to cool down the atmosphere. It's going to interact with water, cause acid rain. This surrounding area is going to get covered in ash, And that's pretty much it for this unit. So go ahead, let me know if you guys